Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. Dr. Chris, we'll start off with one from Dom, who's actually on holiday. But he says, could you answer this question? What does limescale remover contain and how does it work to remove the limescale? Chris?
Well, to understand how limescale remover works, it's good to understand, first of all, what limescale is, because it's a big problem in the southeast of England when we have where we have very hard water. Water hardness comes in two forms. There's what's called permanent hardness and temporary hardness. Permanent hardness are calcium and magnesium salts, which are in the water in a soluble form. Temporary hardness are bicarbonates of calcium. So in other words, calcium bicarbonate, Ca and then HCO3 twice. And what happens when you have water with lots of bicarbonate dissolved in it, and this comes from acid rain falling on chalk, for example, and filtering through the chalk and dissolving some of the chalk, which is calcium carbonate, and taking it through in the water. What's actually happening is that when you heat the water up, that bicarbonate is unstable, and it decomposes when it gets hot, for instance, on the element of your kettle, and this breaks apart the HCO3 bit. And what you get is some H2O, a water molecule, and a CO3, a carbonate group. And so you get CaCO3, calcium carbonate, which is chalk. So instead of being soluble, it becomes insoluble, and it does it where the chemical reaction happens, the decomposition of the bicarbonate, in other words, on your kettle element or on your boiler radiator or wherever you've got the heat source coming in. And because it's insoluble, it just builds up and builds up and builds up, and it forms a layer which makes it harder for the heat from the surface to get through and into the water, so it reduces the efficiency of your kettle or whatever it is that the limescale has furred up in. How do you get rid of the limescale? Well, you have to try and reverse that chemical reaction somewhere. You've got to put something energetic in, which is capable of driving the chemical reaction back the other way and making something insoluble. So you've got to turn the calcium carbonate from an insoluble salt back into soluble products. The way that most limescale removers do that is by using an acid, because acids, as long as they make a soluble product, will react with the calcium carbonate, and they fizz, as you'll have noticed. If you put some vinegar in your kettle, for example, the fizzing is that the acid, which produces hydrogen ions, H+, attacks the carbonate group, the CO3, and it breaks it down to make a water molecule, H2O, and a carbon dioxide molecule, CO2. And the carbon dioxide comes fizzing off, that's the fizzing you can see, and because water is just water, you turn something solid, the calcium carbonate limescale, into something that's gaseous, CO2 that bubbles away, or and a water molecule. The other way of doing it is you can use a phosphoric acid or something. Phosphoric acid's a good one, it's in Coca-Cola. It makes Coca-Cola have a certain texture and flavour and a sharp taste. If you pour that into your kettle, you will make calcium phosphate, and this too is soluble, and it dissolves in the water in the kettle, making the limescale disappear. Then you pour away this very calcium-saturated solution, but you've got a nice clean kettle element. So most descalants have some kind of acid in them that reacts with the limescale, produces either CO2 or a soluble product.
Excellent. Thank you, Dr. Chris. Let's move on to our next question. Now, in fact, a couple of people are quite worried about the oil. First of all, Mark in Dunstable has said, would it be possible to make some sort of extra length of pipe that can move on the other pipes by remote control so that if there is a hole in the oil line, this pipe can be navigated to the hole in the pipe, and then the compress around it to stop the leak may be by using the underwater pressure to compress this outer pipe. Patrick has asked, why isn't this oil floating on the water? There's lots about it in the newscasts. They've mentioned underwater oil plumes. Many people assume that oil always floats on water. Can you tell us why it doesn't in this case? Phew, there's a lot there, Chris. Go for it.
Yeah, so just to recap, which is perhaps what BP are trying to do underneath the Gulf of Mexico, 5,000 feet down, very, very deep water. They have drilled a hole in the seabed. Normally there is an arrestor which is placed on top of that hole, the purpose of which is that in precisely the situation that's occurred here, if there's some kind of pressure surge or some kind of breakage, then the arrestor closes and this caps off the wellhead so that the oil can't escape. For some reason, this has broken, and when there was a problem and the rig blew up, the oil now had a superhighway coming out of the reserve of oil, the big amount underground, and it's connected straight to the sea, so the oil is surging out. Now, because the oil is coming out so quickly, although oil is less dense than water and would normally float on water, and indeed quite a lot of the oil is floating on the water if you look at the pictures of the aerial photographs of the Gulf of Mexico, because the oil is under pressure underground and it's less dense than water, so wants to rise very quickly, it's coming out of that hole so fast that it's making enormous amounts of turbulence, little vortices like whirlpools in the water. And this is drawing the oil out into the water and fragmenting the oil into lots of little miniature droplets, which are less buoyant than the big sheet of oil would normally be. And they're therefore forming these underwater plumes, which are being carried away by currents deeper in the water, and that's why we're seeing these underwater plumes. The other reason that there are plumes of oil going along under the subsurface is because they've been adding various detergents to the oil. The way in which you deal with an oil slick, because it's floating on top of the water, is you disperse the oil using detergent molecules. And the way detergents work, it's exactly the same in your washing up bowl when you put the oily chip pan or something in and put some washing up liquid on. What the washing up liquid has in it is a hydrocarbon molecule, so a long wiggly chain of carbon atoms linked together, at one end of which has usually something like an acid group which loves water. And this has the effect of having an oily bit that loves oil chemically coupled to a water-loving bit, so the oily bit can grab some oil molecules and the water-loving bit pulls them into solution and makes them dissolve. So you can make an oil that wouldn't normally dissolve go into solution. And because they've been spraying these detergents and dispersants onto the oil slick, it's now forming these little globules which are sinking down into the water, and then at some point they're equalising or equilibrating in terms of density in the water, and then they're being carried along underneath. So that's why you've got these seams. The current way in which you need to deal with this disaster, and this is what BP are trying to do, is one, to mitigate the immediate problem, and this is what's costing them between 13 and 20 million a day, which is about equivalent to how much they're making in profit. So basically they're currently spending all their profits on the clean-up operation. So they need to deal with the immediate problem straight away, which is, of course, mitigating the impact on the environment and on the wildlife. And then number two is how do you actually make the situation on the seabed safe in the long term? And the only way really to do that, despite all the good ideas and the things they have tried to do, is to drill another hole into it, because you've got to get the pressure off, because it's the pressure that's underground that's forcing the oil out. So if they can get another well opened up and another hole in there and start pulling the oil out, then the pressure will drop sufficiently that the oil will stop coming out of that hole and go up the new one, which of course is connected to a suitable receptacle.
All right, well, let's go to this one now. Dr. Chris, if you contract prostate cancer, are you more at risk at getting testicular cancer as well? Chris?
So the question being, if you have a diagnosis of prostate cancer, are you more at risk of getting a diagnosis of testicular cancer? I wouldn't have thought so. I'd have to check to see if anyone's done a proper follow-up trial on this, but my inclination is to say no, because testicular cancer tends to be a cancer much more common in young people. It has a peak age between 20 and 30, I think, and the problem with prostate cancer comes on in much older individuals. The peak is around 60 to 80 in men there. So I think that there's epidemiology on my side saying that no, this is unlikely, and also they're two different organs. Although they are in the same sort of neck of the woods anatomically, they are not connected, although, that said, hormones provided by the testes can influence the growth of prostate cancers, and sometimes it's necessary to give drugs to shut down those hormone systems in order to reduce the rate of growth of the prostate cancer, and that's one way of dealing with the problem, but there's no direct link between prostate cancer and testicular cancer as far as I know.
Excellent. Let's go to email this time. David from Birmingham says, can the body become enormously strong when under stress? Chris?
Well, this is the Incredible Hulk scenario, isn't it? When someone goes into some kind of stressful environment and then they develop this superhuman strength or find this strength they didn't know they had. I don't think there's any evidence that this really exists, apart from the fact that when people are very, very, very motivated to do something, then obviously they will try a little bit harder. But I don't think there's any evidence that there's this sort of untapped reserve inside our body that we just don't tap into normally, and then suddenly, when the mind or mood takes us, we can suddenly exploit it. The reason for that being, thinking logically, if you had all of this muscle bulk and all this hidden strength in you somewhere, you'd have to have energy going into maintaining it and keeping it there. And that would be so costly for the body that it just couldn't afford the waste. It's a bit like you having half of a house you don't live in, but keeping the heating on there anyway. It would just amount to a huge electricity and heating bill that would be pointless. So the body doesn't work like that. So I think it's probably unlikely.
This time, Mr. Heaney says, always a great show. Dr. Chris, how much water should an adult of over 70 drink each day to keep really well? Chris?
Well, we have what are called insensible losses of water. Insensible means losses you can't do anything about. So most people pass out a litre or two of urine every day, and breathing means that if you're doing a lot of exercise, you can lose half a litre just in the air that you breathe out, because the air is moist, because it's saturated, it's been in your lungs, which are full of water, and that's why when you breathe out on a cold day, you see condensation. That's all the water that's coming out of your body. You breathe in dry air, you saturate it, breathe out wet air, you're losing water. So that's about up to half a litre a day. Plus there's other things that you lose. Water from sweat on a very, very hot day, especially if you're exerting yourself. Some people can lose up to 5 litres an hour in sweating.
Wow.
And also when you go to the loo, the number 2, you lose some water that way, because digestive juices you secrete into your intestines, litres and litres of digestive fluids and juices every day. Most of it gets reabsorbed. A few hundred millilitres probably goes out through the back passage every day. So if you tot that lot up, you need to make sure you balance out the amount you lose by taking more back in. But there is a hidden side to this, because just by breaking down food and breaking down sugars in food, you get some free water anyway, because the chemical formula for glucose is C6H12O6, and if you burn that with 6 oxygen molecules, 6O2, what you end up with is a load of energy. You get 6 molecules of CO2, carbon dioxide, that you breathe out, plus you get 6 molecules of H2O, good old water. So just by breaking down sugar in the body, you get some free water just through having your metabolism running. So most people need to drink a couple of litres a day. I don't think there's any hard and fast rule. If you're losing more water because you're active, you need to drink a bit more. If you're less active, you need to drink a bit less. You shouldn't force yourself to drink if you're not thirsty. Humans are the best adapted animal on Earth to tolerate water deprivation. So all this idea about you have to drink X amount of water every day, otherwise you're going to dehydrate and pass out, it's just not true. And unless you have had some risk factor, such as kidney stones, because you need to keep your kidneys flushing water through, for example, to make sure you don't have stones, or urine infections where you should drink a little bit more to help flush out the infection, other than that, you should drink what you're comfortable with.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Going back to the email, and I think the name is Saipo, actually, who's asking, how is or was HIV virus formed in the first place? Chris?
Well, yes, the question of where HIV came from or comes from is a really important question. Now, most people, when you think about viruses, they think, well, it's probably something that's been around for thousands of years. But with HIV, we actually have a really good idea as to when this agent first popped up. And it's really recent. It first appeared in humans probably in about 1900. Now, the reason we know this is because people have gone hunting for old samples that are locked away in people's laboratories and freezers. And the first sample that came to light was a part of an epidemiological study that was done in the 1960s and 70s in Africa. And this was tested, and HIV was found in this sample. And scientists were able to compare the genetic signature of that HIV agent with what's doing the rounds in humans today. And they were able to show that there are a number of important changes, because as HIV spreads and goes from one person to the next, the genetic material in the virus slowly accrues small genetic changes, mutations. And these occur at a certain rate. And so we can work out what's called the genetic clock of an infecting organism and work out how long it must have taken from one thing to turn into another thing. And because they knew that sample was collected in the 1960s and they had the sample from today, they could work out how fast the genetic clock of HIV was running and therefore make predictions as to where it must have come from, because we know that there are animal viruses, including viruses in chimpanzees called simian immunodeficiency virus, SIV, which share very, very close homology. In other words, genetically, they're very, very similar to HIV. And this shows that they must have been the origin of HIV. And so you can work out on the basis of how fast HIV changes when it must have come from SIV, which is its immediate ancestor, to go into humans. And that date is around about 1900. And some samples that were found in the Democratic Republic of Congo and analysed in the last 5 to 10 years have also corroborated this origin of HIV, and scientists have been able to work out the mutation rate and the genetic clock of HIV. What made it jump into humans? Well, the favoured theory is that probably people butchering and eating bushmeat, chimpanzees that were infected with their version of HIV, SIV, a person got a chimpanzee, got its blood on them and had a cut, and the chimpanzee blood got into the person's bloodstream, and this carried the chimpanzee virus into the person, and that virus mutated in the person and turned into HIV, and that person then spread the virus to their friends and relatives, and it then began to spread in humans. Now, this has probably happened many times in the past, and this may sound strange to people to think, well, how do we know that HIV has evolved many times? There's actually several types of HIV circulating in the human population at the moment. There's HIV-1, which is very, very common in the West and in Europe and America. There's HIV-2, which is very, very common in bits of West Africa. And occasionally you see cases of it in Europe. So that shows, because they're two different viruses, they must have made this jump out of chimpanzees and into people more than once. So why does this happen, and why did it start to spread? How did it suddenly become this massive problem? Well, the answer is it's actually down to population and urbanisation. This was probably happening many, many times in isolation in bits of Africa for many, many years, where this virus was jumping out of the chimps and into people, but it was never a problem. It wasn't until Western civilizations went to Africa and set up colonies, and those colonies became big cities, and with big cities come all kinds of problems like prostitution, lots of fast transport with roads connecting one centre and another, and trade, and then you've got lots of people in close contact with lots of other people, and they can begin to infect each other, and then it carries it around the world. And that's where we think HIV came from. And it wasn't really until the 1980s that suddenly it cropped up in the West in a big way, and in a certain group of people with certain risk factors, and that's when we realised we're dealing with a whole new entity here, and that's when the virus was first identified by Robert Gallo and Luc Montagnier, who got the Nobel Prize, actually, in recent years for it.
All right, well, something a little bit connected to that. Dr. Chris, Marilyn loves the show, and she says, why is anemia so common in places like Africa, more so than others, and is there a definite cure? Chris?
Well, anemia means you haven't got enough blood, and specifically don't have enough red blood cells. And red blood cells are the little cells that have haemoglobin in them, and that's the stuff that carries oxygen around the body, and it's got iron in it. So various parasites love blood, because if they drink blood, it's got lots of protein and it's got iron, both of which animals need to grow. So mosquitoes drink a bit of blood for that reason, and they drink blood when they're mating and laying eggs, because they need to have a high protein and high iron diet. But mosquitoes don't make people anemic. But there are various other parasites that can. And in places like Africa, people may have a very high burden of intestinal parasites. One particular species of hookworm, for example, there's one called Nicata americanus. And these little worms have an amazing life cycle. The adult worm is probably about an inch or inch and a half long. And it lives in the intestine with its mouth latched onto the wall of the intestine. And it's got these little teeth which pierce the blood vessels there, and little bits of blood come off, and the worm drinks the blood, and that's its food. And periodically it sheds some eggs into the intestine, and the person then leaves those eggs wherever they go to the toilet, and those eggs hatch into larvae which sit in the soil waiting for a person to come along. And they seem to be able to sense when a pair of feet or a bit of skin is nearby, and the larvae go onto the skin, they're microscopic, and they have this amazing, it's almost like a drill, and they drill through the skin, and as soon as they go through the skin, they then get into the bloodstream, and they go round in the bloodstream until they get to the lung, and they come out of the bloodstream and settle in the lung, and they begin to grow, and they grow from this little larva to an adult worm in the lungs until they're about an inch long, and then they crawl up to the person's throat where they trigger coughing, and the person then coughs up the worm into the back of the throat and swallows it. And then it goes down into the intestine, which is exactly where it wants to be, and it hooks on. And these worms can live for 10 years. And so as people carry on acquiring more of them from the environment, they then end up with maybe 20, in some cases up to 50 of these worms living in the gut, and they're all drinking a little bit of blood. And this can make a person eventually become iron deficient, and then they can develop an anemia. Another reason why people might have an anemia in third world countries is for dietary reasons. If people aren't getting a good enough diet, and it takes a lot of energy to make blood, and it takes iron to make blood, if you've got a poor diet, this can also threaten you, and you can end up with an anemia. And another important thing to consider in parts of Africa, and this goes back to where I started, which was mosquitoes, there are certain individuals in the population in African countries who have a genetic disorder which is called sickle cell anemia. This is where they have a gene, or a change to their hemoglobin gene, which makes their red blood cells go into a sickle shape when they get low on oxygen. This particular change in their hemoglobin makes their red cells an unattractive and inhospitable place for malaria to grow. So these people have this genetic problem, which makes them a bit anemic, but on the other hand, it also means they're protected from malaria. So they're therefore in the population at a much higher level than they would normally be, owing to evolution, because this bad thing, this sickle cell anemia that they've got, at the same time protects them against an even worse thing, which is malaria.
Now then, we got a lovely question here from Jennifer, and I know just the feeling with that, Jennifer. My mum used to say it was just growing pains, but she'd ask, she's from Colchester, she said, is there such a thing as growing pains, Chris?
Yes, there are. I think Jennifer's age says it all, really, because growing pains are when you are growing, and when you do most of your growing is when you're in your teenage years, when you go into puberty, and the hormones that are made in ovaries and testes, depending upon whether you're a girl or a boy, kick in, and they trigger the body to start developing very fast. And the way in which we grow upwards is that in the long bones, things like the femur, for example, the leg bone, your thigh bone, there is a lump of cartilage in the middle of it called the growth plate, and this contains special material and cells which make a cartilage model of the bone, and then special bone-making cells move in there and fill in the gap and add the bony material. And when you go to bed at night, when you're growing at your peak rate of growth, then this expands and you lay down extra bone, you're stretching your bones and making your bones longer before they come in the next day and get turned into solid bone material. And this stretches everything. With that growth also means that the loading across various joints and the work muscles are doing is also having to change quite dramatically, and therefore it's not surprising to feel a bit achy when you've got so much growth going on and you've got all this new bone being made. So the answer is yes, it is a real entity. For most people, it's not a major problem. There are some people who get knee problems. There's a condition called Osgood-Schlatter disease, and this is where you get a sort of ridge in the underside of the kneecap, which can make your knees a bit uncomfortable. Luckily, most of these things are temporary, and you just have to stop growing, and then hopefully the effect goes away. Girls are in for a luckier time than boys because they actually stop growing a little bit younger than boys because they start growing younger than boys. So usually girls get over the problem a bit sooner, and then they can start enjoying their latter teenage years without having to get aches and pains. But good question, Jennifer. Thanks.
Now, Malk has actually returned something to you. He says, that's very good, but it doesn't actually tell us what SIV is or how it originated or how exactly chimps got it or what it does to them. Chris?
SIV is simian immunodeficiency virus, and this is an identical or chimp equivalent to HIV, and it seems to affect the chimps in an identical way to the way that HIV affects humans. For a long time, scientists thought that it was relatively benign in chimpanzees. It's not, and chimpanzees who are infected with it, which they catch in exactly the same way humans do. It's spread by various routes, sexual ones, injuries, fighting, that kind of thing, where there's blood-to-blood transfer, that kind of thing. It affects the chimps in the same way as HIV affects a human, by destroying the immune system over time. Other members of the primate and monkey families also have different versions of this SIV, and in some of those it genuinely is less nasty. It seems that the animals have evolved to live with this virus rather than to be killed by this virus. HIV too, as I mentioned earlier, doesn't come to us from chimpanzees, but a related species called the sooty mangabe, which is another primate species. But it's very, very common in all these animals. We don't know exactly where it came from, but it almost certainly has an ancestor way back in early days of mammals, because you can find equivalent immunodeficiency viruses for many other species. You can find feline examples. There's feline immunodeficiency virus, FIV, and many others. So the answer is that back in history somewhere, there will be a virus that adapted to become SIV, and it eventually got into humans through our contact with chimpanzees.
Right. Thank you for that, Chris. Now, Dr. Chris, says Ian in Wyndham, do all objects expand in heat? I know metals certainly do, but what about plastics and organic things like bones in humans, etc.? Also, what exactly causes expansion to occur? That's from Ian in Wyndham.
Well, actually, it's not entirely true that all objects expand when they get hot. There are some metals that are a bit weird and buck the trend. Gallium does this, bismuth does this, and antimony does this. And it's interesting because bismuth is a very interesting metal. When you heat these things up, they actually turn into a liquid, and the solid floats on top of the liquid, a bit like ice floats on water, which is very bizarre. And no one quite understands why this happens and why this density change should occur. Why should there be a difference in density between the liquid and the solid? Why should the liquid be more dense? But it would appear that the liquid forms can attract the atoms of the substances closer to themselves than the solid form does. So the solid is a more open or loose structure, and this makes it less dense because there's more space, whereas in the liquid the atoms are closer together. But we don't know exactly chemically why that happens, but it's exactly the same reason that ice floats on top of water, because in ice the water molecules are more spaced out from each other, which actually means the ice, the solid, takes up paradoxically more space for the same amount of atoms, and therefore the density is lower than the equivalent water. Other materials that expand, there are many things that do behave in these strange ways. Scientists are interested in them for the obvious reason that they may have all kinds of applications, but those metals are quite an intriguing exception.
Now then, Lawrence in Ipswich has sent an email in. Hello, Lawrence, nice to hear from you. How is a rainbow formed?
OK, well, rainbows are an optical illusion. They're a trick of the light, and they require a couple of ingredients. One of them is a nice bright sun. The other ingredient is a rainstorm. And what you need is the sun shining at a dark sky with rain in it. So, in other words, you have a nice clear view of the sun coming from one direction, shining with this dark backdrop. And the rainbow will form on that dark backdrop. Because what's happening is that rays from the sun, remember that white light from the sun is actually made up of lots of different wavelengths of light, in other words, lots of different colours of light, and when you mix them all together you see white, but in fact there's all those different colours mixed in. And when the white light goes into a raindrop, it goes in through the front of the raindrop, it bends a bit, because when light travels from one substance, air, into another substance, water, it slows down or refracts, and this makes it bend, and different wavelengths of light bend a slightly different amount to other wavelengths of light, and as a result the different wavelengths go inside the raindrop, bounce off the back surface of the raindrop because it looks like a mirror. You must have seen, if you go underwater in a swimming pool and look at the surface of the swimming pool above you, it looks like a mirror. Well, that's exactly what the inside of the raindrop looks like to this light wave going into it. The light bounces off that mirrored surface at the back of the raindrop, comes back towards the front of the raindrop, goes out into the air again, bending or refracting a bit more as it does so, and then it comes towards your eye. And because those different colours have all been bent by a different amount, it spreads them out in the sky, and you see a pattern of rings inside each other, and because we're only seeing half the circle because of the direction we're looking at it from, it would actually be a circle if you could look from the right direction, but we see half a circle because the land gets in the way. Then you see the light spread out into the different wavelengths, all those different colours.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.